Greetings. My name is Abhishek Yadav, and I am a fourth year student in Vellore Institute of Technology, Chennai, and I'm in specialization computer science and technology. This is my digital assignment 3 for blockchain and cryptography. The topic that I'm going to speak about today is Diffie-Hellman key exchange. Let's start with this. The topic of today's discussion is going to be DFE Hellman key exchange. So Whitfield Diffie and Martin Hellman are called the inventors of public key cryptography. So DFA-Hellman key exchange is the first public key algorithm that was published in 1976. So let's first start with the question: what is DFA Hellman? So basically, what DFA Hellman is, it is a public key algorithm, and it is only used for key exchange. What DFA Hellman does not do, it that it does not encrypt or decrypt any data or any messages. And DFA Hellman algorithm is based on discrete logarithms, and due to its security advantages, it is widely used in security protocols and commercial products. Also, Williamson of Britain's CESG claims to have discovered several years prior to 1976. So, DFA-Hellman was published in 1976 by Whitfield DFA and Martin Hellman, and Williamson of Britain's CESG claims to have discovered it several years prior to 1976. So as we can see, as we know that DFA-Hellman is based on discrete logarithms. So moving on to discrete logarithms. So what is logarithm? So we have example here. We have log base 10 100 equals 2. So because 10 raised to the power 2 is 100. So in general, if we have a notation of log base m b equals a, then we can generalize our output as m raised to the power a is equals to b. So where m is called the base of the logarithm, and so this is what logarithm is. And now what is discrete logarithm? So a discrete logarithm can be defined for integers only. So for discrete logarithms, our m and b are going to be integers only. So in fact, we can also define discrete logarithms mod of p, where p is just any prime number we can choose randomly. So, what is the advantage of discrete logarithm problem? So, the security of DFA-Hellman algorithm depends on the difficulty of solving the discrete logarithm problem, commonly referred as DLP, in the multiplicative group of a finite field. So we will come back to this. We will move forward and know what this basically means once we are comfortable with groups in finite fields. So moving on, we have sets, groups, and fields. So a set is any collection of objects called a set is any collection of objects called the elements of the sets. So what is an example of set? So basically we have real numbers, we have integers, and moving on, if we can define an operation on the elements of the set, and certain rules are followed, then we get other mathematical structures called groups and fields. So what we do is, if we can define an operation on the elements of the set, so if we have a relation or a function that follows a certain rules, or mathematical then we a certain rules or are followed, then we can derive some mathematical structures which we call groups and fields. So coming on to groups, so a group is a set G with a custom defined binary operation plus addition operator symbol, such that the group is closed under uh, the operator. So that is, for a comma b which belongs to group, is basically means that every element in the group AB, if we add it, should also belong to the group G. And then these groups follow associative law, and the associative law holds that is for any A, B, C belonging to G, A plus B plus C is A plus whole of B plus C is equals to A plus B whole of A plus B plus C. And there also in a group there also exists an identity element 0 or any identity element such that A plus 0, 0 is just a symbol to represent the identity element. So A plus 0 is equals to A. So also for every element belonging to the group, there exists an inverse element of A. We can symbolize it as minus A, such that if A operation minus A is done, then we'll get the identity element or 0. So, if for all A, B belonging to G, A plus B is equals to B plus A. So, then the group is called an abelian or commutative group. So, if a group follows this property of A plus B is equals to B plus A, then it is called an abelian group or a commutative group. If a group G has a finite number of elements, then it is called a finite group. So more about group operations. So plus does not necessarily mean normal arithmetic addition. So plus is just a symbol for an operation, and plus just indicates a binary operation which can be custom defined. Yeah, so we can have division, we have negation, we can have modulus, we can have and we can have XOR, and then the group operation could be denoted as dot. So let's not confuse ourselves with addition symbol, and now we can just denote group operations as dot. So the group notation with plus is called the additive notation, and the group notation with dot is called the multiplicative notation. So basically, these are the two notations of the groups. So the first one, the addition one, the plus one, is called the additive notation, and the group with the dot one is called the multiplicative notation. Coming on to fields. So a field is a set F with two custom defined binary operations plus and dot such that the field is closed under plus and dot, that is for A comma B belonging to the field. So basically what it means is a field is a group, is basically a set that follows two group properties, which is the additive group and the multiplicative notation. Additive notation group and the multiplicative notation group. So basically it follows all the rules, like A plus B also belongs to F and A dot B also belongs to F. The associative law also holds. Sorry for the inconvenient pause. So, yeah, so we were on the, so basically, we were on the associative law that holds. So, for a field, the associative law also holds for any A, B, C, which belongs to F. A, addition operator plus whole of B plus C is also equals to A plus B, whole of A plus B plus C, and it also follows for the multiplication law, which means A dot whole of B dot C is equals to whole of A dot B dot C. So also for every field there exists identity elements. For addition operation we can say we have 0, and for multiplicative operation we can have 1, such that for every operation for every A belonging to F, when it is when the binary operation is performed with these identity elements, the result is A itself. So A addition or A plus 0 is equals to A, and A dot 1 is equals to A. So the field is a group a field is basically a set that is true for both of the groups. So for each A which belongs to F, there also exists an inverse element denoted by minus A, or A reciprocal reciprocal of A, such that A plus minus A is 0, and A dot reciprocal of A is equals to 1. So basically, for if a element is is a element is perform is a if a element is performed a binary operation with its inverse, then we'll get the identity element of the group. So as you can see, a plus minus a is equals to 0, which is the identity element of multiplication, and a dot which is the identity element of addition, and a dot reciprocal of a is equals to 1, which is the identity element of the multiplication notation. And just like groups, if a field F has a finite number of elements, then it is called a final field. So moving on, we can just come back to the discrete logarithm problem, and then it will be more clear to us. So the security of Diffie-Hellman algorithms depends on the difficulty of solving the discrete logarithm problem in the multiplicative group of a finite field. So now we know what a multiplicative group is, and we know what a final field is. So moving on to examples of groups. So let's see. So set of real numbers are under the operation addition. This is one example of group. Another example would be set of real numbers are under operation uh, under the multiplication operations. Similarly, we can have integers under addition and integers under multiplication. Then we can have some integers modulo a prime number p under addition, and we can have integers modulo a prime number p under multiplication. And also we can have 3 by 3 matrices under addition, meaning matrix addition, of course, if it's a 3 by 3 matrix, and a 3 by 3 matrix under multiplication, and it means matrix multiplication. So fields, let's say, uh, a set of real numbers are under addition and multiplication. So is an example of field. Set of integers z under addition and multiplication, and let's say set of integers modulo prime number p under both addition and multiplication. So generator of a group. So if A belongs to a group G, all members of the group can be written in terms of A by applying the group operation star on a number of times. Then A is called a generator of the group G. For example, let's say 2 is a generator of let's say 2 is a generator of Z star 11, and 2 and 3 are generators of generator of Z multiplication modulo 90. So Z star 11 represents integers, the set of integers on a binary operation of multiplication modulo 11. So 2 is a generator of Z star 11, as you can see in the table. For m 1 2 3 4 5 6 7 8 9 10, we have a function, we can just have a generator of 2, and 2 raised to power m mod of 11, we can create the values. And for z raised to power 19, we can do we can say same for 2 and 3, as you can see in the table. So moving on to primitive roots. Yeah, so primitive roots. If x raised to power n is equals to a, then a is called the nth root of x. So for any prime number, let's say p, if we have a number a such that power of a mod p generate all the numbers between 1 to p minus 1, then a would be called the primitive root of p. So in terms of the group terminology, A is the generator element of the multiplicative group of the finite field formed by mod of P. So then for any integer B and the primitive root A of prime number P, we can find a unique exponent I such that B would be equal to A raised to the power I mod of P. The exponent I is referred to as the discrete logarithm or index of B for the base of A. So this is power of integers modulo 9, and I've take 18 values of A, and this is the the power of the a, like a square, a cube, a to the power 4, and after the results of the exponents, then we calculate the modulo of 19. Also, there's a table of discrete logarithms of base 2, modulo 19, and with base 3, and then in the seat figure we have base 10, in D we have base 13, for E we have base 14, and for F we have base 15, and for each and every figure the modulo was 19. So, moving on, Diffie-Hellman algorithm. So, basically, coming back to Diffie-Hellman algorithm, so there are five paths on Diffie-Hellman algorithm. So, first is global public key elements, then user A key generation, user B key generation, generation of secret key by user A, and then generation of the secret key by the user B. So, global public elements. So, Q is your random prime number, and alpha, which is basically less than Q, and alpha is a primitive root of Q, which is also the generator of a group. So, the global public elements are also sometimes called the domain parameters. Moving on to user A key generation. So, first, what we do is we select private XA, and XA would be less than Q. After that, we calculate public key YA. So we calculate public key YA using the private key that we generate. So YA is basically generated as alpha raised to power x of A mod of Q. So this is the public key generation for user A. So that's why X A. So similarly, we can generate the private and public key for user B. First, we'll randomly generate X private key XB, which should be less than Q. Then for that, we'll calculate the public key for the user B. We'll calculate YB as YB is equals to alpha raised to power X of B of user B mod Q. So, generation of secret key by user A. So, this is how the generation of secret key by user A would be done. So, this is the formula. So, K is equals to Y of B. So, Y of B was your public key of user B raised to power X of mod of Q. So, this is your secret key by user A, which is generated by using the public key of B. And this is your secret key generation by user B, which uses the same formula, but instead now it uses the public key of A and the private key of B and mod of Q. So how this goes is Diffie-Hellman key exchange. So first, what user A is do is generate a random XA which is constrained to less than Q from the private key of user A. We calculate the public key of user A using the formula alpha raised to power X of A mod Q. Then we send the message along with the public key, and then user me gets the key. Then it generates a random XB. It calculates YB, the public key for its own, and then calculates the secret key. And the secret key is calculated by the public key of user A and raised to power the private key of user B mod Q. And then it is sent back public key, the message is sent back along with the public key to user A, which also calculates the secret key using the public key of user B raised to the power of private key of user A mod Q. So this is a Diffie-Hellman exchange example. So we have chosen Q as 97, and we have chosen alpha as 5. XA is the private key of user A, so 36, and XB is the private key of user B, and we have chosen it as 58. So we generate YA. as alpha raised to the power xa. So alpha is 5 raised to the power xa 36. So we get that as 50 mod 97. Then we calculate yb, which is basically alpha raised to the power uh, xb, which is basically equals to 44 mod 97. And for your secret key generation for k, we have public key of b. For user a, secret key generation, we have public key of user b raised to power xa mod q. So for that, we have 44 raised to power 36 mod 97, which is basically equals to 75 mod 97. And then we have the secret key generation for user B, which uses the public key of user A raised to power private key of user B mod Q. So we have 50 raised to power 58 mod 97, which equals to 75 mod 97. So why Diffie-Hellman is secure? So opponent has Q. It ha he opponent They have Q, they have alpha, they have YA, and they have your YB. To get XA or XB, the opponent is forced to take a discrete logarithm. So the security of a Diffie-Hellman key exchange lies in the fact that while it is relatively easy to calculate exponentials modulo a prime, it is very difficult to calculate discrete logarithms. For large primes, the latter task is considered infeasible. So just adding the discrete algorithms to your normal signing algorithms, it makes like it unfeasible to calculate your XA or XB, provided that you have the parameters that is shared by every node in the system. So with that, I would like to conclude my video. Thank you.